So today we're going to be looking at data structures. Now you can get pretty far in programming without understanding data structures, but eventually you're going to need to know them, understand how they work and when to use them. And that's what we're going to be covering in this video today. So let's get started. A data structure, as the name implies, is a structure for holding data. When you're writing a program, you're always going to be dealing with data and need to have a way of storing it. The simplest form of a data structure is storing a single value in a variable, but eventually you're going to need to store multiple values. And depending on how many values you've got, how you store them is going to affect the performance of your application. Once you understand the different data structures, you're going to have another tool in your tool belt that you can use to write better programs. As the saying goes, if all you have is a hammer, everything looks like a nail. Treating everything like a nail is going to lead to poorly designed software with bad performance. Different data structures have different uses, so you want to make sure that you're using the right one. The simplest data structure, and the one that we've already covered in one of my other videos, are arrays. Arrays are simply multiple values stored in memory. The key thing to remember is that in most programming languages, arrays are stored in what we call a contiguous block of memory. What I mean by that is that arrays are stored all together in one block of memory. When you create an array, you need to specify how big you want the array to be, either by specifying a number or by initializing it with the initial elements you want to put into it. This is because the computer needs to find a block of memory large enough to store your array. If it can't find a block of memory big enough to store your array, then it needs to free up some from somewhere else. All of this sort of memory management takes up quite a lot of time and costs you performance in your application. Some programming languages do give you the methods to be able to add and remove items from an array. Now, even though you can do this and the programming languages make this easy, it is going to cost you in performance. Every time that you want to add or remove an item from an array, the computer needs to find a whole new block of memory for that array to sit in, and then free up the memory that was originally taken up by your array. This, of course, all adds up and can be quite computationally expensive if you're doing a lot of adding and removing in your program. When I think about this memory management in my head, I kind of think of it like booking seats at a cinema. Say you've got a party of 6 that all want to see a movie. So you go on the website and you book a big block of seats so all of your party can sit together. Then a couple of days later, your friend says, "Oh, I want to see the film too." So you go on the website and you find other people who booked seats right next to your seats. Therefore, to be able to fit all 7 seats in, you need to find a new place in the cinema to sit. Now the computer is doing exactly the same thing every time you add an item to an array. Arrays are great when you need to iterate through all your items, either for mathematical operations or for looping through items in your code. Because they're stored in one block of memory altogether, it's a lot less taxing on the computer when it needs to go from one item to the next. However, if you are going to be adding or removing lots of items in an array, you might be better off with a list. Lists are a bit like arrays in that you can store multiple values in them, but they do allow you to add and remove items more easily. Unlike arrays, you don't need to specify how big your list is going to be to start off with. You can essentially consider a list as an auto array. It's still an array under the hood, you can still store multiple values in it, but it will auto manage all of that memory management for you. In most languages, lists are just over-allocated arrays. Instead of reallocating memory every single time an item is added, a list will allocate more memory than it actually needs, usually twice as much. This means a lot less memory management when you're adding items to your list. It's not just the memory allocation that's a bit different with lists. Lists tend to store references or pointers to the values that you're using. In languages like Python, this means you can store different data types of different sizes in your list, unlike an array where all of the items need to be the same data type. Lists are great if you're going to be adding and removing lots of items in your code, but if you're just going to be reading the list sequentially, an array is always going to be a lot faster. Unlike an array, which can just store the data, a list is going to be reading your values from different parts of memory, which is going to be a lot slower. A list also takes up a lot more memory than an array does. A list stores the count and the references and the data as well. The next data structure we're going to look at, which are really useful, are queues. Now, queues are a bit like lists in that they use arrays under the hood, but they act a bit differently. Now, queues work on a first in, first out basis, a bit like queues that you have in real life. New items are added to the tail of the queue, and then items are read from the head of the queue. Unlike arrays and lists, with queues you can't read stuff from the middle of the queue. You always have to read them in the order that they went in. Queues are mostly used for scalability reasons or whenever you need to read something in order. They're especially useful if your computer can't keep up with the number of requests, but you still need to process them in the order that they come in. For example, let's say that you've got an API endpoint that takes a photo and turns it into a cartoon. Now you have a website that allows a user to upload the photo. The API then takes the photo, does a few image manipulations, a few filters and turns it into a cartoon and returns it to the user. Now let's say your website goes viral and suddenly your API can't cope with the number of requests that it's getting. This is where queues come in. When the user uploads their photo to the API, instead of all the work being done in the API, you can add the photo to a queue, and then a worker can pick up that image and do all the image manipulations that it needs to do, add any filters, and then return it to the user. Then if you start getting more requests than you expected, you can just spin up more workers to deal with the queue faster. Queues can be used as data structures in your code if you need to process things in order, but generally they're used in infrastructure for scalability. So we have covered various ways of storing multiple values in a data structure. But what if when you're adding those values, you want to avoid duplicates in your code? This is where a hash set comes in. Now, a hash set, as the name implies, takes a hash of your data and stores the data against that hash. This prevents any duplicates from being added to your hash set. Now, the key difference between a hash set and the other data structures we've looked at is that a hash set doesn't store things in order. A hash set will store things in the order of the hash and not the order that you inserted it. Hash sets are perfect when you need to avoid duplicates in your data, but they're not so good if you need to have things in a certain order. Next up are dictionaries. Now, dictionaries are very similar to hash sets in that they stop you from having duplicate values in your code. However, unlike hash sets, they work on what we call key value pairs. Now, what do I mean by key value pairs? Now, if you think of a real dictionary, you use it to look up a word and find its meaning. Now, in this case, the key would be the word that you use to look up, and the value would be the meaning. So dictionaries basically allow you to store a key and look up a different value. Key value storage, like dictionaries, have so many different uses in programming. They're often used for things like caching, but they're also used in things like NoSQL databases as well. Dictionaries are also really good if you want to have things like memory lookup tables in your code. Now, dictionaries are a form of hash map. So when you store something in a dictionary, the key gets hashed, and then it's the hash that is used to look up the value that you're storing. As you probably guessed, hash sets also use hash maps as well underneath the hood. Where a dictionary will store the hash of the key, a hash set will store a hash of the value. Like a hash set, dictionaries aren't stored in order of insertion. This generally isn't much of an issue as you're going to be using the key anyway to retrieve values from it. If, however, you find you do need an ordered dictionary, most languages do offer this as an option. Next up, we have linked lists. Linked lists are another way of storing multiple values in your code. As the name suggests, linked lists have each item linked to the next one, and they usually have it linked to the previous one as well. Unlike normal lists and arrays, there's no way of accessing a particular item within a linked list. You have to traverse it from start to finish. Linked lists aren't stored in memory as a contiguous block like they are with arrays. Instead, each item has a reference or pointer pointing to the next item in your list. This is really useful as it means you can add new items or remove them without having to reallocate memory from the entire list. This, of course, makes insertions and deletions a lot quicker and a lot more predictable in how long they will take. You can even insert an item in the middle of a linked list, as all you need to do is change the node on either side of the item you're adding in. Linked lists are perfect if you're going to be adding and removing a lot of items and you want to ensure that the time it takes to do that is constant. This is something which is crucial for real-time applications where every single millisecond counts. Typically, linked lists are used to implement things like queues or stacks where you're going to be accessing the items in a certain order. Another way you can use to store data in a structured way are trees. Now, trees are more like family trees than they are the green kind. They allow you to store not only the value, but also the relationship as well. A tree will have one root node, which then has one or many child nodes. It's a bit like a linked list, but it allows for more than one relationship. The number of children each node can have will generally depend on what type of tree you're implementing. For example, general trees can have many children, whereas binary trees can only have two. There are many different types of trees, so there's binary trees, there's binary search trees, there's red-black trees, and there's AVL trees as well. Generally, trees are really useful for storing data that has some form of hierarchy to it. For example, a HTML or XML file generally has items with parents and nested children. This could be stored as a tree, as can like the files and folders on your computer or like a company hierarchy structure. Trees are used extensively in database indexes, domain name servers, machine learning, and search algorithms. Most programming languages, however, don't come with a ready out-of-the-box tree that you can use. You generally have to implement it yourself. This is because there's so many different ways to implement a tree that is very use case specific. Finally, the last data structure we're going to look at are graphs. Now, graphs still have this sort of relationship that trees do, but they lack that top-down structure. Now, if a tree is like a family tree, a graph is more like a social network. There's no root node at the top of a graph. Each node can have more than one relationship, and that relationship can go both ways. In fact, most social networks like Facebook or LinkedIn will use a graph to store the relationship between its users. If you find in your data that each node is related to multiple other nodes, then you might need to look at a graph to store your data. Again, like trees, programming languages don't come with graphs generally built in. This is something you have to build yourself, generally using things like arrays and linked lists to do that. These are the 8 main data structures that you're going to be using in your code. So next time you're building an application, have a think of these in mind and see which one would be most applicable to what you're building. I hope you enjoyed this video. Thank you for watching, and I'll see you in the next one.